It's important to note that geometry is all around us. What I'm showing you here is a plumb bob string that you can just barely see to show you the idea of a line. This is probably a more useful one to you. You've seen situations like this where they've been showing a football game and they will show you the runner's foot being very close to the line. A line doesn't have any width. The line is where the green stops and the white begins, or the white stops and the green begins. This is sometimes called the sideline, this white part, but that's 6 feet wide so that players don't stand on it. The only people that are allowed to stand on that are the referees. So the runner is in bounds if his foot is on the green. He is out of bounds if his foot is on the white. So that is an idea of a line. One of the things that I was trying to show you is that in some cases a line we think of as going on and on forever. This is a road in Australia that I checked, and it goes 54 miles without having a turn, but yet it is not truly a line because a line continues forever. One of the things that people sometimes talk about is that the north-south lines on the globe actually go straight north and south, and most of the times they do, but I'm showing you here that every so often they have to make a correction. At 42 degrees, about 30 minutes north latitude, or north longitude, this is, no, it's north latitude, sorry. This is the place where the north-south lines are corrected. And if you notice at this spot, they're off by 365 feet. If you go a little bit farther east from there, they are off much, much, much more. Here is how far they are off just southwest of Manson, Iowa. And you can see that's almost it's almost a third of a mile off. This is west of that spot where we were before. But from here, these lines keep on going north until you get to the Minnesota border, and then at the Minnesota border they make another correction of about almost a half a mile. And that is at 43 degrees 30 minutes. So we were at 42 degrees 28 minutes, 43 degrees 30 minutes. So about every degree or so they have to make the correction. Now you can really see the correction here in the map of the counties in Iowa. Every county along this line has a correction, and if you notice, the correction over towards Sioux City is quite a bit. If you were going, as you were going north, you would have to correct and go west quite a bit to keep on the line. And then over here on the eastern part of that line, you can see there's not very much correction at all. And in fact, if you go way east in Iowa along that line, here's Waterloo. Over almost by Dubuque, there's hardly any correction at all because that that line was probably one of the main north-south lines, and so they didn't need to correct very much at all there. One of the things that we are talking about is a ray. A ray starts at a spot and goes out forever in one direction, and if you notice, these rays start at the sun and they go outward from the sun, and as they do, they form angles. And if you notice, the vertex of the angle is here at the sun, and the farther away they get, the more spread out they are. Now, it's important to note that rays are easy to understand that they go forever and ever, because how far would you have to go before the sun would quit shining? Well, that's kind of a trick question, because the sun rays go forever. They launched a spacecraft in 1977 when I graduated high school that is now beyond Pluto, and so when it turns and takes a picture back of the sun looks like a regular, just any other star. and Earth doesn't appear at all. They couldn't make that satellite with solar panels because there isn't enough sunlight after a few years. Actually, they didn't think it would last anywhere near this long. It has a nuclear power reactor, and it's still transmitting back. You can look it up. Pioneer, probably about 17 or something like that. Here is another angle. This is in my garage, and it's the angle between the roof truss and the sidewall truss. Now, every angle has a measure, and the measure of this angle is about, to figure out what the measurement is, you start over here at the 0, so we're following the bottom numbers over, and we get to about 110. Here's 115, so it's about 116 degrees. So this angle here is 116 degrees. Interestingly enough, this angle over here, you can tell how big that angle is. Well, maybe not yet, but you will be able to in a few seconds. So if that's 116, why don't you write down a guess on what you think that other angle is? This shows two lines that are parallel. This line of the carpenter's square is parallel to the line of the roof, and the way I did that is I measured down. I put the blade of the square up on the roof, and I measured down to the end of the tongue, and I made a mark on this upright, and then I did the same thing over here on the end of the tongue on this one, and then I connected those two marks together. Next lesson, we're going to figure out why that worked. But for right now, you can know that these two are, this line is parallel to the roof, which you can't actually see. This plumb bob, although it doesn't look like it here, actually hangs straight down. Because of that, it is always perpendicular to the earth. So no matter where you are in the world, the plumb bob will hang straight down. So here's the world. Every single spot, oops, that's not straight down. Every single spot on the earth, the plumb bob hangs straight down. Here is another angle I'd like to show you. This is the angle that a telephone pole makes with its guy wire. That guy wire is pulling down in this direction because the post naturally would be pulled over into the street. If you notice in the background here is another pole, and I've got a picture of that one here, and on that picture you can see, this is from the other direction, you can see this post is pushing the pole back. Now what we should do is we should measure those two angles to see what those angles are. Let's see if we can measure those two. So I'm going to measure this angle, and you can't see my measurement because it's not on the screen, but when I measure it, I get about 40 degrees, 39 degrees. The thing is, though, you can't really tell that because the angle is way up here in the air, and I'm looking up at it, so I'm not measuring it exactly what the angle is in real life. Let's look at this angle here, and when I measure this one, I get about 36 degrees. I wonder if there's any relationship between those two angles, why they are both right around 30, 38, 37, that size angle, 39 and 36 degrees. Here is a bridge truss, and if you notice, I'm sorry, a railroad bridge, and if you notice there's an angle here between the overhead and the side of the bridge, and that angle on here is exactly 60 degrees. I wonder if there's any reason why it's exactly 60 degrees. This angle here shows the overhead, which is parallel to the ground, compared to this support beam here, and then they are tied together to the main support with a gusset. I'm going to see if I can find the angle there between those two, and it looks to be about 55 degrees. Here is another angle on the bridge. These two, the cross member and the upright, are perpendicular, and this cross member here, we would say, is forms two separate angles that are complementary because they add up to 90 degrees. The angle between these two is 50 degrees, so the angle between these two will be 40 degrees. Well, it's not quite 40, but that's because I'm looking up at the angle again. Let's try it again. This angle is, it's difficult to say because, it's difficult to say because I can't quite see where those two interact. Yeah, it's right around 50 degrees. Next one. I think this is important because it shows, well, I should turn this so that you can see the picture the right way. This shows a triangle, but more importantly, it shows two parallel lines. The bottom support and the top support are parallel, and it's cut by a transversal. Here is the transversal, the upright. There's another transversal that supports the wire on the other side. In either case, these angles are equal. I'll draw these sets of angles that are equal based on these parallel lines. So on the top, we know that these two lines are parallel. This line and this line are parallel. In the one case, this is the transversal, so this angle is equal to this angle. This angle is equal to this angle, and so on. The other transversal is this one over here, and this angle is equal to this angle, alternate interiors. It's actually also equal to that angle because these two angles are corresponding angles. And then this angle down here is equal to this angle down here. So parallel lines cut by a transversal, and they do that for a very important reason, and that is they want these supports to hold the wires up in the right way. If you notice, there's also a guide wire here. I'm going to measure how big that angle is. Oops, no I'm not. Yeah, I am. Lost my protractor temporarily. That angle is about 40 degrees. Once again, right around that 39-40 degree mark. Here's more angles on that same bridge, and if you notice, in some cases they are held together by turnbuckles. In other cases they're separated by these cross bars. Up at the top you can see there are a number of cross members holding them together, and these cross members form vertical angles so that this angle here is equal to this angle, and this angle is equal to this angle. Those angles are vertical angles. Here's another cross member, and if you notice, I'm sorry, this is the inside of the upright, and it's showing that they tie these two sides together using a number of triangles. And if we measure the size of those angles, we find that each of the angles is 60 degrees. Actually, no, it's not. It's oops. Let's see here. each angle, oh, that angle is 40 degrees. Oh, I keep switched. I can't use my touch screen. Oh well. Here you see some more cross members on the other side. I thought I'd show you this to show another spot where you have parallel lines that are cut by a transversal, and these angles at the top are equal to the angles at the bottom. What's interesting is that in the next lesson we're going to see that they form parallelograms. The other thing I'd like you to note is that these distances along the bottom are all equal. From here, each of these sections is equal, and we are going to learn that they make these sections up here equal also, as long as these lines are parallel, joining the ground member to the member that's supporting the bridge, the seats. Next, here's another set of vertical angles. I thought this was kind of an interesting picture because it shows that the vertical angles here in the back, this is actually parallel, so these two angles are equal, and actually all four of these angles are equal. But what's interesting is in the next set forward, these angles are equal because of the alternate interiors of parallel lines cut by a transversal. Now, the reason that they're equal, though, is that each of these angles in the middle is also equal. So what you end up with is a bunch of, and we're going to learn about it next time, a bunch of congruent triangles. In other words, these triangles out here on the outside are congruent, and I'm going to draw way down on the inside. Let's see if we can get one of these. I'm going to draw this one right here. Let's see, it's this triangle here is congruent. You can't see the other part because it's up underneath the, but anyway, they all form congruent triangles. Now, the reason why those braces go all the way to the top is that makes that causes the least amount of strain on the uprights. So in other words, these cross members being as long as they are make for a very, very stable triangle here, and they are indeed bolted together in the middle. Here's another example of two parallel lines cut by a transversal. This is a street in Eau Claire, and actually here is the parallel lines right here, this one and this one. I'm going to show you that they are parallel. Now, actually, they should have run the street all the way over like this, but in both cases they turned it right here at the corner. And so here's the transversal. So this angle here corresponds to the angle to the other angle. Those two angles are corresponding angles. The reason I know that is we used to live in this house, and people would come to this house and ask for us, and people would come to our house and ask for the people that lived in the other one. And you might wonder, well, why did they do that? Because those two corners looked a lot alike. Now, in actuality, our houses certainly didn't look alike. This is the house down the street from ours. It's got a one-car garage. It's got a little tree out front. And then our house, this is where we used to live, has a tree over here, but it's a two-car garage. It's white. I mean, there's a lot of differences. Oh, by the way, I built this shed in the backyard and put the little cupola up on top. That was my adding to the neighborhood. Here's another spot where we show parallel lines. These are roof rafters in my garage. And you see this line up here is parallel to the bottom of the rafter. I'm sorry, meets up with the bottom rafter, and each of these upright members is parallel. Well, what's true down at the bottom is that they are 16 inches apart. We can figure out how far they are apart at the top, and we're going to do that when we talk about rise and run and triangles in next lesson. Here's another spot though. Oh, I'm sorry, here are the lengths of the different uprights. This first upright is 85.5 inches tall. The next one is 77 5/8 inches tall. Then 69.5 inches tall. And then 61 5/8 inches tall. Here's another spot in Eau Claire that I think it's important for us to look at to see how parallel lines work. In this case, we can measure, because these lines are parallel, each of these streets are parallel, we can measure, now we aren't going to use that last one, but if we measure the distance here, and the distance here, and the distance here, we will be able to figure out what the distance here is if we know one of the other two, or the distance here, or the distance here. So let's take a look at it in Google Earth, and I'll show you what we're talking about here. We have to get up to Eau Claire, and it's over on the, ooh, that's Wausau, went too far. And it's over on the west side. Let's see, around here someplace. There we go. So what we can do is, let's get the, I want to look straight down at it rather than at an angle. And let's find those different measurements. So the first measurement that I'm going to find is, yeah, we're in feet. Okay, let's find the measure from this street here to, oops, from this street to this street is 273 feet. Okay. Then let's measure the distance from here to here, and it's 273 feet. And the distance from here to the edge of the road, which you shouldn't go all the way to the edge of the road, is 153 feet. Then let's measure each of these. Well, so we have to go from there to the edge of the road where we were before, 182 feet. Here is 329 feet, and this should also be 329 feet. Well, they get 327 feet, 329 feet. So you can see how that mathematics works. Let's let's go to the next slide. And we're supposed to bisect an angle. Well, what I did is, after the angle was drawn, I measured out 3 inches in both directions. And then once I had measured out 3 inches, I checked to see that I made this distance over on this side, where the 3 inches was, exactly equal to this distance on this side. If you notice, it's 1 5/8 inches on each side. So this would be the cross spot, and I could draw a line joining those two points, and it would look like that. That is the bisector of that angle. We're also supposed to trisect an angle, and this took a little bit more work, so I'm going to show you what I did to trisect an angle. The first thing I did is I drew this angle here, which you can see is 70 degrees. Then I put this line into the diagram right here, so that this distance is 2 inches. Why is that so important? Because once I had that, if I know that from here to here is 2 inches, and I'm perpendicular over here, I can make this 4 inches. 2 plus 4 makes 6. And so if this part here would be 2 inches and this part here would be 2 inches. And then I can draw my trisected angle right here. And if you notice, they came out to be 41.5 degrees and 22.5 degrees, which I think if you add those three up, you get 70 degrees. Let's see what else is there. And I think that's it for this lesson.